Right, in this we're going to look at how we can do some analysis of our seabed raster, our elevation raster, which is called a digital elevation model, to calculate some other qualities to our terrain. So we're looking at seabed. We've got this raster of elevation from GEBCO, and what we're going to calculate from this is two things. One is roughness, how complicated the seabed is. So is it smooth, which might indicate there's sediment, or is it rough, which might be reefs? And the other thing we're going to look at is slope. So where is it steep and where is it flat? So two different qualities we're going to work out from that depth raster. The roughness we'll do first. That's more straightforward. So if we first go up to raster and then analysis and then down to roughness. And it asks us which layer we've got coming in, which is our depth raster. And then we just have to say where it needs to go. So choose a spot. And you see I've done this before. I'm going to put it in there. I'm going to call it roughness 1. It's going in a folder within my GIS file called depth analysis. And then run that. Doesn't look too exciting at the minute, but it's produced a map, and you can see, like already, you can see where these white areas are, where that's where the underlying terrain might be quite complex in the way that it's going up and down. You can change the symbology on that if you want to have a look at it a bit more easily. So I'm going to go to properties, symbology, change it to single band pseudo color. I'll classify that, just apply, just to switch that around so you can see it a bit more clearly. If you zoom in, you can see even though it's looking quite plain in some of these areas, as you zoom in, you can see a bit more detail. Right, so that's that one. It's very similar for doing slope. We again go to raster and analysis and then down to slope. So the only thing that this is slightly more complicated in is this bit here, ratio of vertical units to horizontal. And that's complicated slightly because of the coordinate system we're using. It's something you've got to bear in mind. So we're using a version of the World Geodetic System, WGS 84, and that measures your position on the Earth's surface by longitude and latitude. And each degree is actually quite a big distance. So there's, each unit of measurement, east and north, are quite large, covering big chunks of the Earth's surface. However, the height is measured in meters. So that ratio of vertical units to horizontal is not 1-to-1, which it's saying there. If you're working in something like the British National Grid, it's great because your eastings and northings are all actually measured in meters. So the ratio is still 1, which makes it a lot easier. But for the World Geodetic System, then you've got to think about this. So luckily, clever people have worked this out for us. If I go to here, bring it up. I might have to close that. So what we need to know is the Z factor for our particular part of latitude. So that relationship, because longitude gets smaller as you go further and further north, it's going to differ, the Z factor, the ratio between the measurements and the height, depending on your latitude. We're at 50 degrees approximately. So our Z factor, I'm going to pick this one. And that's all very well, but that's actually flipped from what we want it to be. So basically that's saying there are 0.0001395 degrees to a metre. And what we want to know is how many metres there are to a degree. So I just divided by 1 to get this relationship. So there's 71,664 metres to a degree. So that's what we need to put then into here. Okay, so if I go back to my raster, So instead of 1, we've got 70,000. Don't need all those decimal points. Doesn't need to be that accurate. Right. So that should give us some sensible measurements in terms of degrees of slope. So slope is going to be from 0, which is flat, up to 90 degrees, which would be vertical. And then again, I've got to tell it where I want to go. So not save to a temporary file. I want it to save to one called slope. Okay, and close. So let's have a look at that. And we can see that the slope goes from 0 to 34. So that's heartening because it's saying that black is flat, which looks about right, doesn't it? Most of our seabed would be black. And it's going up to 34 degrees. Remember, 90 would be vertical. So there's not too many features that are going to be near vertical in natural landscapes. And this is suggesting that we've not got any, really. But that seems like a sensible amount of degree range. Again, we can make it more visible with our symbology. If I go to properties, and just change that back to our single band pseudo-color. Again, so we can see now where there are areas. So it looks quite similar to the roughness one, in fact. Because it hasn't displayed properly, that is. Right. There we go. Right. If I get rid of the land, you can see, because this model extends actually up onto the land, you can see where it gets quite steep up on the mountains in Scotland and things, which is quite fun to look at. But we don't need those bits. So that's got our 2 layers, extra layers. So now we can take data of depth, how steep the seabed is and how complex the seabed is, and add that to our basking shark sightings using the point sampling tool. So that's the next step.